Question 4. We have a merry-go-round. Like this. Here. And its axis of rotation is here. Going around like this. And it is being ridden by 2 children. One is 19.5 kilograms and the other is 17.5 kilograms as shown. Both are sitting at the outside edge of a ring that has a mass of 54.5 kilograms and a radius of 1.3 meters. The father gets them started by pushing at the outside edge with a tangential force of 288 newtons through an angular distance of 110 degrees. In an ideal situation without friction from the bearing in the middle, what would the angular speed of the ride be after the force is removed? So, we can write everything that we're given again. M1, M2. Now for the ring. Mass is going to be 54.5. Radius is going to be 1.3. For our push, this is 288 newtons. Our angle theta that's equal to 110 degrees. Now converting this to radians, that's going to equal to 1.9199 rad. First thing that we have to do is we have to find the total moment of inertia. So, inertia of the ring is equal to the mass times the radius squared. That's going to be 54.5 times 1.3 squared. This is going to be equal to 92.105. And what we want to do is we want to treat the children, our point masses, at the radius. That means that we can use I of the kids and set that equal to M1 plus M2 times the radius squared. They're the same radius from the center, 19.5. 17.5 times 1.69. This is 62.53. Now that is going to be 62.53. Do that. Now in total, we have 154.64 kilograms times meters squared. Now we can start on part A. We want the angular speed after the force is removed. So we want the work done by father first. So we know that the torque is equal to F times R. That's 288 times 1.3. That's 374.4 newtons times meters. Now the work done by the torque is R times theta. That's 37.4 times 1.9199. That's 718.6 joules. Now we need our rotational kinetic energy. that's 1/2 154.64 omega squared 71877.32 omega squared. Omega squared is 9.29. Omega is equal to 3.05 rad per second. Now, for part B, if the final angular speed is actually 3.02 radians per second, what is the frictional torque that exists in the ride? So, we know that our actual speed is omega 3.02 rad per second. And then we know our actual KE is equal to 1/2 154.64 times 3.02 squared. That's going to equal to 705 joules. Now we can calculate our energy loss to friction. So we take our energy, 718.6 minus 705.6, 7.5. And that's going to equal to 13.6 joules. So our friction work is equal to torque times the friction, the torque of the torque from the friction times theta. Torque F is equal to 13.6 divided by 1.9199. That's equal to 7.08 N times M. Part C. Given this frictional torque, how many revolutions will this ride make before it comes to a stop after the father's force is removed? So, we know that after force is removed, we know that the initial kinetic energy is going to be 705.0 joules. But then we know that friction torque removes energy until stop. Work is equal to torque F theta, 705.0 is equal to 7.08 times theta. Theta is equal to 99.6 rad. Now we want rad in revolutions, so we're going to divide this by 2 pi. That's 15.9 revolutions. A solid sphere, hollow sphere, ring, and solid disc are all released from rest at the same height, 61.5 centimeters from the floor. All roll without slipping down a ramp that is 1.85 meters long. All have the same mass and radius. What is the linear speed? What linear speed does each object's center of mass have as it reaches the bottom? So, say we have an incline like this. And we have a cylinder. So, that's our height. That's going to be L. So, we're given that height is 61.5 centimeters. That's equal to 0.615 meters. And they all roll without slipping, and they have the same same radius. So we can use the idea of energy conservation. So at the top, energy is going to equal to potential. And then at the bottom, energy is going to equal to kinetic energy in its translational form and rotational form, because it's going to be rolling without slipping. So some of it's going to be converted into rotational form. So we can write with energy conservation, there is no friction. Therefore, we set the initial equal to the final energy. That will be our PE. And this is going to be mgh. And we can use our no slipping condition. We can substitute that in right there. So we're going to have that mgh is equal to 1/2 mv squared plus 1/2 moment of inertia times v squared over r squared. You can factor out our 1/2 v squared. And then if we solve for v and we take the root, that's going to be 2gh divided by 1 plus I over mr squared. Now after this, we can compute gh, substituting in our values. This top part is going to be 12.054. We can write the moment of inertias of the disks of the different objects. So for a solid disk, we can record that I is equal to 1/2 mr squared. So that means that here, if we have I over this is going to be 0.5. I is equal to mr squared. So if we have I over mr squared, that's going to equal to 1. I is equal to 2 over 3 mr squared. I over mr squared is equal to 0.667. For solid sphere, we have that if I is equal 2 over 5 mr squared, 1 over mr squared is equal to 0.4. Now for a solid disk, we can compute so everything is the same. 2gh is going to be constant up there. And we just have to fill in the I mr squared component for all of these different shapes. So for solid disk, V is equal to now for its result, this is going to be 2.84 meters per second. Now for ring, V is equal to 12.054 divided by 2. That's going to equal to 2.46 meters per second. Now for the hollow sphere, V is equal to the root of 1.054 over 2, which is going to be over, not 2, 1.667. This is going to be 2.69. That's C. Now solid sphere. V is going to equal to the root of 12.054 over 1.4, 2.93 meters per second. So now that we have all the values, we can compare which one finishes first. Fastest means largest V. So solid disk is going to be first place. Ring is going to be 2.4. Okay. Ring 2.46. It's going to be a 2.00 kilogram pole, 2.6 meters long, is initially situated in a straight up position connected by a frictionless pin. It begins to rotate from rest and falls through the final position where it is perfectly horizontal. Consider the pole to be a long, thin rod. So this is going to be A. And we're going to consider this to be L over 2, and this is going to be L. Given that our mass is 2.0 kilograms and our L is going to be 2.6 meters, it's going to be a uniform thin rod, and it's pivoted about one end. This is our pivot, and this is the center of mass, and the initial is vertical, finally is horizontal. So the drop in center mass of height, we know that the center of mass is at L over 2. The height of the center of mass initial is above the pivot, which is equal to L over 2. Now the height of the center of mass final is equal to 0. Therefore, the change in the height of the center of mass is L over 2, which is 1.3 meters. First, we're asked what is the angular speed of the pole as it passes through its final position. So this entails, we want the angular speed at horizontal. So using energy conservation, no net external forces, no friction. We have mg change in height is equal to 1/2 moment of inertia omega squared. Now we know that the moment of inertia of rod about an end is equal to 1/3 ml squared. If you plug this in for this I here, you're going to have that mg delta h, or we have our delta h over here. What we can do is we can cancel the m. So now solving. Now plugging in, we have but we want the root rad per second. Now what we need is the tangential speed of point A. Now we need the torque about pivot horizontal. At the horizontal, you have the weight of the center of mass, and you have the pivot force that is going through the pivot, and it's providing no torque. In addition, we have torque due to Fg and our lever arm. Now we have to find our horizontal. Torque is equal to IA. We know that therefore now finally we can find the E. So at the final position, we have our weight that is downward to the center, which is a long arrow. And then we have a pivot force upward, but it's going to be longer than the weight since it also has to supply the centripetal acceleration. So the torque is only from the weight. The pivot force is going to be greater than the weight. The pivot force is going to be up. And the weight force is going to be down. A yo-yo is released from rest and allowed to fall from a person's finger. Consider the yo-yo as a uniform solid disc of mass 58 grams and radius 7.0 centimeters that the ring wraps around the other outer radius. What is the speed of the yo-yo center of mass after it has fallen 39.0 centimeters? H of drop now for the inertia of a uniform. And the string, it's gonna wrap around the outer radius. So no slipping. You can use your no slip condition. So we can draw this. This is our string that's wrapping around it. Downward is going to be mg. Upward is going to be our force of detention. Mg has to be greater than t because it's going to accelerate downward. So you can write Newton's second law, F. Now you can write your rotation equation. You can use your no slip condition. You can substitute this in. Now you can substitute in I. Now you can plug this into Newton's second law. We have our torque. Our tension. Therefore, solving for A. Now we can use kinematics. No, V initial is equal to 0. So therefore, (2.26 meters per second).